Hi everybody, welcome you by Pantech eLearning platform, your digital learning simplified with a happy e-learning. Let's start reducing air pollution in our surrounding areas. To do so, as a kickstart by electric vehicle. Now let us see about the EV car prototype hardware testing, phase 1 testing in this video. We'll be having a e-vehicle. For that we need a charging point. That charging point can be derived from the solar or from the wind or from the boat. And the team involved in this prototype initiator is Mr. Malayapan and testing as Balraj and supporter Sudhagar and Sasi Kumar. We are conducting EV Masterclass, 30 days Masterclass by Mr. Malayapan. In that you will be getting more information about how to design in detail. To get more information, subscribe Pantech eLearning and get information updated. Next, let's see the basic introduction, what we are going to see in this video. EV is an electric vehicle. For this, here we are going to see the basic prototype of EV design, which includes vehicle chassis, that is the wheel with a motor and body. Here we have used PMDC Motor, permanent magnet DC motor, and the controller unit we have used, and their display unit, and the controlling mechanism is speed, brake and direction, speed increase or decrease, and the driver module to power up to give the pulses to the power circuit, and there is a battery unit, and next the protection unit, and in later days the security system and implementing advanced autonomous vehicle. Next, let's see the basic block diagram, what is going to be implemented in this prototype. Here the controller we have used is DSP controller, and that controller gets the input from the controlling mechanisms, direction and speed and braking, and the display unit displays what are the operations going to be undertaken. Next, the TLP250 driver board. The pulses generated from the DSP controller is given to the TLP250 driver board, and this TLP250 driver board and the controller are powered up by an isolated power supply. Next, the battery 24 volt battery system. Here we have used a 24 volt DC motor, so we have used a 24 volt battery system. From that we are going to convert to 15 volt using a DC to DC converter, and it is fed to the isolated power supply. And from that 24 volt battery system, it is given to the fused protection circuit, and from there it is going to be fed to the main power circuit, and from the main power circuit it is the load is connected to the main power circuit. This main power circuit is going to be controlled by the pulses generated from the DSP controller, which is fed after the TLP250 driver board. Next, the speed feedback. The speed is sensed and displayed using the display unit, and then charger. We need to charge the 24 volt battery system, so there is an external charge controller. Next, let's see in detail about the controller used in this, the controller unit. Here we have used the DSP-30F4011 controller. This controller is used to generate the pulse to drive the motor with the help of H-bridge chopper power circuit. So the pulses are generated according to the chopper circuit. And then this controller is used to get the inputs to drive the vehicle safely. Actions are taken by the controller is displayed using the display unit. This controller is going to perform three major tasks. One is forward running, reverse running and braking. Forward running in the sense speed increase or speed decrease, and if you are going for a reverse running mode, the speed increase and decrease, and then the braking, regenerative braking. Here is the pin configuration about the DSP-30F4011 controller. Here there are 6 PWM pins with the dead time for the complementary pair pins, and there is a 9 analog or digital pins we can able to use it, and there is a capture pin. This capture pin is now here, it is used to sense the speed from the motor. The speed sensors are externally connected. By using a proximity sensor we are going to measure the speed, and it is going to be displayed in RPM using the display unit. Here this is the customized DSP-30F4011 controller PCB what we have used in this prototype. This PCB is going to generate the pulse for the e-vehicle. Controlling keys and display units are connected externally. And next, the driver unit used for the power devices. This driver unit is present in between the controller and the main power devices. That is, this driver board is going to isolate and amplify the pulse generated from the controller, and it is going to be fed to the power devices. Because the power devices, the controller produces the 5 volt pulses, so this 5 volt is not enough to switch on and off the power devices, so it is going to be amplified, and moreover the power devices are going to be operated at a high voltage, so the controller is going to be operated at a lower voltage, so there need a isolation. So this TLP250 driver board will provide isolation and amplification. There is a gate protection also provided in this unit. Here there is a basic TLP250 circuit diagram. Here this is a TLP250 IC, and there is a Darlington pair to amplify the pulses, and there is a zener to protect the reverse voltage, and there is an indication LED to know about the pulses, whether it's on or off, but generally we will be using a kilohertz, so the LED will be almost on if you are going to continuously switch on and off. In this point we will be providing the input pulse from the controller, and here this point is going to be fed to the power devices. And here there is a TLP250 driver board image. This TLP250 driver board we have used in this prototype, and there is a simple waveform, that is the pulse. The pulse given from the DSPIC30F4011 controller over here, and the pulse input is almost the 5 volt pulse, and the output is from the output of the TLP250 driver board, and the output of the pulse will be around 15 volt. The frequency will be same as input, but the voltage level alone will be increased, and the isolation is provided by the TLP250 driver board. Next, let's see the pulse generation method what we have used in this. In this we have used the 4-quadrant operation. In the first quadrant, the motor shaft will be rotating in the clockwise direction, and the speed and torque is in positive, so the motor is in forward motoring action. And next, in the second quadrant operation, the forward braking is going to be applied. That is, we are going to stop the shaft rotation, so the rotation speed is in positive and the torque is in the negative. Rotation speed is in positive and the torque is in the negative, and this is a second quadrant of forward braking. And in the third quadrant operation, the motor shaft is going to rotate in the reverse anti-clockwise direction, and the speed and torque are going to be in the negative direction, so the motor shaft will be rotating at the reverse direction, so the motor is considered as reverse motoring condition. Next, the fourth quadrant operation. Here we are going to stop the shaft again in the reverse braking mode. Here the rotation speed is going to be negative and the torque is going to be in the positive direction, and the fourth quadrant operation is going to be a reverse braking operation. Next, let's see the power circuit diagram what we have used in this. This is a basic 4-quadrant operation circuit diagram. Here we have used 4 power devices and 1 PMDC motor and a 24 volt battery system or a 24 volt DC voltage. Here M1, M2, M3 and M4 are going to be act as a power device. This is not like a normal inverter circuit. This circuit diagram we have used to control this motor, PMDC motor. Next, let's see the pulse generation method. For the forward motoring operation, here there is a small animation. This will explain how the motoring operation is done in the forward motoring condition. Here the switches M1 and M4 are going to be in conduction. That is, here according to the circuit diagram, the M1 and M4 are going to be in conduction. Let's see how it works when we are going to apply the pulses to these MOSFETs switch on and off. Here, let us consider the time division at particular time, say 1 millisecond or 5 millisecond or 100 microsecond. Let us consider for 100 microsecond. For 100 microsecond, the M1 and M4 are going to be switched on. So the path will be, voltage will be flowing from M1, positive voltage from M1 and then to the motor positive terminal and then to the negative, and it closes the loop by using M4 and to the ground. That is a negative point. And during the operation of next 100 microsecond, M1 is off and the M4 is on, so there won't be any contact from the positive terminal. It will be closed from the ground alone, so the motor will be, field will not be energized, so the motor will not be running. Then again we have applied the positive terminal for M1, switched on M1 and M4. Again the loop exits and the motor rotates in the positive direction, that is forward direction. While we are applying from the M1, here this portion is going to be act as positive and this is going to be ground, so the motor will be running in forward direction. And again M1 is off, M4 is on. Again M1, M4. So continuously it takes place. So when it is going to be take place like this, the motor will be running at a particular speed. So this on time we are going to say it as a duty cycle. So the total time is going to be considered from on time and off time. By adding both on and off time, we are going to calculate the time division. If we reduce the on time, then the motor speed will be reduced. To increase the duty cycle, that is if we consider for 100%, in 10% it will be running at a minimum speed, and at 90% the motor will be running at a maximum speed, provided the input voltage should remain constant. So here we are going to use a battery, so almost up to some extent the battery will be supporting and the speed will be continuously running at the same speed. Next, for the reverse motoring operation, here there is another animation. Here the M3 and M2 are going to be switched on and off. This graph X is going to be a time division and Y direction is going to be voltage. So 0 to 5 voltage, that is I have considered from the controller unit. Suppose we are providing, if you are going to visual by using a driver board output, then the voltage level will be around 15 volt. Here the same circuit diagram we have used, and the M3 and M2 are going to be switched on and off. Here the M3 and M2 are switched on first, so the positive voltage is going to move from the through M3 and it is given to the second terminal of the motor, and the first terminal is connected to the M2 and it is closed through M2 and it reaches the negative point. So this motor, the second pin of the second terminal of the PMDC motor is going to be positive and the first terminal of the motor is going to be negative or ground. So the motor will start rotating at the reverse direction. Next, the M3 is switched off, M2 alone is in running condition, so there won't be any voltage, positive potential voltage applied to the second terminal of the motor. So the motor stops and again M3 and M2 are switched on, so it rotates at the reverse direction. Again the M2 alone switched on, M3 is switched off. So by continuous switching on and off of M3 and M2, the voltage applied to the motor is going to be varied. So the same condition how I have said for the forward motoring operation, if we vary the duty cycle, the motor speed will vary. At 10%, if we consider the total time duty cycle percentage is 100%, at 10% the motor speed in the reverse direction will be very slow, and at 90% or 100% the motor speed will be at the maximum. So by continuously switching on and off, the motor continuously switching on and off the power devices, we are going to attain the motor speed rotation. Either it may be a forward or reverse direction. Next, let's see the power circuit hardware image. This is a circuit diagram what we have used, and here this is the main power circuit for the 4-quadrant chopper operation we have used. Here there is the input DC battery voltage is given in this point, and there is a fused protection, and there is a load connection point. Here the load is going to be a PMDC motor. It is going to be connected over here in this PTP termination, and the power devices with heatsink is placed as per the circuit diagram, and they are interconnected using the circuit board. Next, the battery backup unit. Here we have used 12 volt 18Ah lead acid battery. We need 24 volt we need to drive the 24 volt DC motor. So we are going to use 12 volt battery, two 12 volt battery connected in series. So when we are connecting the battery in series, we can able to get 24 voltage, but the current remains the same. That is the 18Ah battery we are going to use it. So the 18Ah will be the ampere per hour, 18 ampere per hour, but the voltage alone we are going to increase when we are going to connect in series. If you are going to connect in parallel, the voltage remains the same and the current going to be increased. But here we are used in series connection. The battery we have used is 18Ah 12 volt. Here there is a symbolic representation. There is two batteries connected in series. The positive terminal of first battery is connected to the second battery negative. and again the terminations are connected like this. So we can able to get a 24 volt DC voltage with the 18 Ah. Next, the motoring unit. Here we have used PMDC motor. The voltage is going to be a 24 volt DC and the RPM maximum is 250 RPM. The power of this motor is 350 watt and it is a geared setup motor. Here there is an image of the motor what we have used. For the single motor there is 4 terminals. 2 white terminals are going to be energized for motor. That is, after energizing this white terminals with a 24 volt battery, 24 voltage, you can able to apply a positive potential to the red terminal and negative potential to the black terminal. First we need to apply a 24 volt for the white terminals, then we can able to apply the control speed by using the chopper circuit across the red and black terminal. So this red and black terminal is going to be connected to our power circuit, main power circuit. Next, let's see about the EV structure what we have used. Here there is a skeletal structure. Here this is the image of the skeletal structure for designing our prototype, and there is a color image. Next, the actual image after generating the structure. Next, let's see about the hardware vehicle control method. That is, before driving this prototype, we need to know how to drive this motor by using the control methods which is applied to the controller unit. For this controlling function of this vehicle, for the control 1 is acting as a forward running selection and speed increase, and for the control 2 reverse running selection and speed decrease. That is, when we are starting the unit, if we select control 1, then the forward running is selected. If we suppose we select the control 2, the reverse running is selected. After that, if we press control 1, speed will be increased. If we press control 2, speed will be decreased. Next, by pressing control 1 and control 2 at the same time, the braking operation is done. Either it might be a forward braking or a reverse braking, the braking operation is done. If suppose we have to move for a forward or reverse from one direction to another direction, we have to reset the controller. After resetting the controller, we can able to select either forward or reverse control mode of operation. Next, let's see the EV CAR Prototype version 1.0 hardware vehicle testing video. This video we have tested first on no load condition. We have tested this EV CAR prototype on no load without touching the wheel on the surface. Vehicle is lifted from the ground surface. Power is applied, so the motor is rotating. Here is the power circuit and driver board and the controller unit. These boards are own manufacturing of Pantech eLearning. Production is done in Pantech eLearning. Next, let us see EV CAR Prototype version 1.0 hardware vehicle testing video on load up to 80 kg in both forward and reverse direction on the flat floor surface running. Here we have tested this prototype, EV CAR Prototype version 1.0 on load up to 85 kg on the flat surface running for the forward and reverse running conditions. Now the vehicle is tested with a dummy load of 30 kg. The vehicle starts moving forward. For testing, the controlling unit is controlled by the hand. This is a candid video when we are testing with our team. Now the vehicle is moving in the reverse direction with approximately 30 kg load. Here you can able to see the loads what we have applied for the vehicle. Now one of our team members is acting as a load on the vehicle and moving the vehicle in the forward direction. He is having the controls on the lap, controlling using hand. The motor is rotating forward, so the vehicle is moving forward. Now the vehicle direction is changed and moving in the reverse direction by the same load. At last he applies the brake. Now my another team member is acting as a load of around 60 or 70 kg. He is controlling the vehicle by the controls. He is using the legs to control the vehicle speed and using the steering to rotate front wheel. Now another team member around 80 kg is moving the vehicle in the reverse direction. He is also controlling the vehicle using legs. Small correction has to be done. That is, we rotate the steering left side, the front wheel is moving on the right side. We rotate in the right side, the front wheel turns to the left. Next, let's see about our future upgraded versions. First, we will be smoothening the control methods. That is, the control methods have to be tuned up and it will be very easy to control this prototype. Next, the enhanced design structure has to be built. We'll be moving on for the upgraded version of the motors like BLDC. Next, we plan to charge the battery unit using the solar panel or micro wind setup. That is, if we suppose we are going to charge the battery by using the renewable energy sources, then the pollution level will be more reduced, because if suppose we need to charge the battery by using a AC supply, conversion of AC or any other methods, that also causes pollution in that production unit. So if suppose we charge the battery unit using renewable energy sources, then we can able to reduce the pollution somewhat higher. Next, implementing the security systems. After that, autonomous vehicle. After that, we will be implementing AI, artificial intelligence. These upgradation are in plan for the prototypes. Thank you all. Thank you once again by Pantech eLearning. Corrections will be done and it will be updated to you through our YouTube channel by Pantech eLearning. For more information, visit our website www.pantechelearning.com. You can also inquire through training@pantechmail.com or projects@pantechmail.com. You can able to contact through WhatsApp or phone call using this number 9840974408. For more information and updates, subscribe and get the information updated from the Pantech eLearning. This presentation video editing is done by Balraj. Thank you once again by Pantech eLearning. Bye.